Hi everyone. In the next couple of videos, we're going to be looking at Chapter 17. In Chapter 17, we're going to learn 2 new hypothesis tests and 2 new confidence intervals. For the first hypothesis test and confidence interval duo, we're going to be looking at the difference between 2 proportions. The best way to learn all of these is with an example. In this example, it says, in a study of the effect of air pollution on lung function, a random sample of 50 children living in a community with a high level of ozone pollution had their lung capacities measured, and 14 of them had capacities that were below normal for their size. A second random sample of 80 children was drawn from a community with a low level of ozone pollution, and 12 of them had lung capacities that were below normal for their size. So first I want you to notice that when we do these calculations, we're looking at the difference between these 2 proportions. And difference in mathematics means we're subtracting. I also want you to see that the proportions that we're looking at come from 2 different groups or 2 different populations. So we have one population of children living where there are high levels of ozone and another population of children living where there are low levels of ozone. So we've assigned P1 hat, so the sample from the high level of ozone, we've assigned that as P1 hat, and that's 14 out of 50. And then P2 hat is the sample that came from the low level population. I have the formula for the confidence interval here for the difference between 2 proportions, not because I want you to do this by hand. You know, I never want you to do these by hand, but because I want you to see the order in which the formula is subtracting, because that's going to be important when we're looking at the interpretation of this. So for these intervals, they are taking P1 minus P2. And remember that when you subtract, if you subtract and get a positive number, then that first number is higher than the second number. And if we subtract and get a negative number, then that first number is lower than that second number. Okay, so let's actually find the confidence interval here. We've got the information from the previous slide here, and we're going to construct a 90% confidence interval. To do this, we're going to use the command 2PropZInt. So just like the 1PropZInt, except for now we have 2 samples, so 2 proportions. We're going to find this command in the same place that we find all of the commands for our tests and intervals, and it's going to be under that stat button, and you're going to arrow over to tests. The 2PropZInterval command is way down at the bottom. So you're going to go to stat, arrow over to tests, and go way down to the bottom. And it's that 2PropZInt. Once you get here, we enter the first proportion as the number of successes over the sample size. So this will be 14 out of 50. And then the second proportion is 12 out of 80. And then we're looking at a C level of 90%. And we will get an interval of 0.00663 to 0.25337. So I want you to remember that this represents the difference from P1 minus P2. And again, because it's a positive value, this means that the P1 is greater than P2. So when it says which group has a higher proportion and by how much, we know that the P1 group is higher. So that's the high level of ozone population. And they're higher by, if we round this, we're going to say 0.7% or 25.3%. So this always starts over. The high ozone level group has a higher proportion of children with a diminished lung capacity by between 0.7% and 25.3%. If we're to formally interpret this, we would say that we are 90% confident that between 0.7% and 25.3% more children living in areas with high levels of ozone have diminished lung capacity. I should say more children on average, actually. We'll leave it like that. So the other thing that we can do with this is find a hypothesis test, and we're going to use the same scenario. So I have the same information here, but I switched up the wording because I want you to see how important it is to think about your symbol for the alternative hypothesis. So in this question it says, do these results indicate that a smaller proportion of children living in areas with low ozone have diminished lung capacity compared to those living in areas with a high level of ozone? Test an appropriate hypothesis test at a significance level of alpha equal to 0.05. So notice that it's talking about how the low ozone level is that smaller than the high ozone level. But when we write this, we write P1 minus P2. So when we go to write the hypotheses, first of all, the null hypothesis is always that there's no difference between the proportions. So regardless of the problem, this is always the null hypothesis. Sometimes instead of writing it with an equal sign like this, they might write P1 minus P2 equals 0. Your textbook might do that. For the alternative hypothesis, again, this is asking if the low ozone is smaller than the high ozone, but P1 is the high ozone. So we're asking, is P2 lower than P1, which is the same as saying is P1 higher than P2. So just be really careful there. This is also can be said is P1 minus P2 greater than 0. Again, I use this side, but sometimes your textbook uses these. So the command is going to be a 2PropZTest, and it's going to run the same way as the 2PropZ interval. And if you've already done the 2PropZ interval, all the information from that interval is going to automatically populate into the test. And we find it in the same space that stat tests. It's just not as far down. So it's number 6. So right here, again, we enter that same information if it's not already there. But I also want to show my work to get that partial credit. And then we would say that P1 is greater than P2. And we're going to get our test statistic, which will be a z-score, and then a p-value. So we have a z-score of 1.8 and a p-value of 0.036. And we can write the conclusion, but before I do that, hopefully you are also doing this along with your calculator and making sure you do it right. I want you to go back and just switch the sign for the alternative hypothesis. So go back to like this part here and just switch it to the wrong sign, right? Switch it to the less than, because you saw in the problem it said less than, so you put a less than. It would be a very common mistake to make. And then I want you to see what happens with the results. You'll find a test statistic that is the same. You're still going to get 1.8 for Z, but your p-value will be the complement of what I have here. So it'll be 96 point something %. And if you ever get a p-value that's that high, you're asking the wrong question. which means that you have the wrong symbol for your alternative hypothesis. You should always get p-values that are around the significance level. Anything above 50% and you're asking the wrong question, you're doing it wrong. All right, so then writing our formal conclusion here, again, this starts over. We would say that since the p-value is below the significance level of 0.05, we're going to reject the null hypothesis. So same conclusion as we had before, right? It's below the alpha level, so we reject the null hypothesis and conclude that there is enough evidence to suggest that a smaller proportion of children living in areas with a low level of ozone have diminished lung capacity. So I just took the wording straight from the problem, but you'd be equally correct to say that the evidence would suggest that a higher proportion of children living in areas with a high level of ozone have diminished lung capacity. So it kind of doesn't matter which one you say as long as you have the correct direction. Okay, so the assumptions and conditions for a 2-proportion-Z test or a 2-proportion-Z interval are exactly the same as they are for the 1-proportion-Z test or Z interval, except for that those assumptions and conditions have to hold for both samples. So here they are. Let's check these on the next test. So usually when we are working with hypotheses tests and confidence intervals, we run a hypothesis test first to determine if one proportion is bigger or smaller or not. And if there is a difference, if we've decided that we're going to reject the null and see a difference, then we look at the confidence interval to see how much of a difference. So I'm going to start here with a hypothesis test, just because that's what you would naturally do. I will say I turn it around in the last example because your textbook starts with confidence intervals always and then goes to hypothesis tests. So in this problem, we have a random survey was conducted of patients with Parkinson's disease. Of 164 patients who said they exercised regularly, 45% reported falling within the previous 6 months. Of 96 patients who said they don't exercise regularly, 49% reported falling within the previous 6 months. Can you conclude that the proportion of patients who fall is less for those who exercise than for those who do not? So I've assigned P1 to be the proportion for those who exercise regularly and P2 to be the proportion for those who don't exercise regularly. And we're going to quickly look at the assumptions and conditions. Again, we have to check both of them. This can be a little bit tedious, but we want to say that both of the samples are random. It does tell us right in the problem that both samples are random. I personally don't know how many people have Parkinson's disease, and of the people who have Parkinson's disease, I don't know how many exercise or don't exercise. This would be like a physical therapy question. So I'm just going to assume that both of those counts are less than 10% of their corresponding populations. I don't know this for sure, but I do think it's a pretty safe assumption considering that we have millions and millions of people in the world. And if that's the case, then I think we can assume that the individuals within each sample are independent. Whenever we're talking about proportions, however, we have to check this success-failure condition. So we take the sample size times the proportion to find the number of successes, and we have 74 in this first sample. And then the sample size times the Q1, which is the complement of the proportion, and we see the number of failures as 90. It should add up to 164, right? The number of successes and the number of failures. Anyway, I did this for both samples, and we find that everything is greater than or equal to 10. So we're going to run the test, which is a 2PropZ test. I don't have a calculator here, so I'm just going to write everything out. Oh, before we write our test, we have to write our hypotheses. So our null hypothesis, again, is always that the proportions are the same, right? The null hypothesis is that nothing is different, nothing has changed. The alternative, because of the way I assigned this and because of the way that this is worded, it's going to follow with the less than that it asks for. Because it says, because I let P1 be those who exercise and P2 be those that don't, and it says, do those who exercise, is that a smaller proportion than those who don't? I'm going to have a P1 less than P2. So when we fill in the information for the test, we need our X1, which is the number of successes, and I have that in the conditions here. But to find it, we take the sample size times the proportion and round appropriately to 74. And then our N1, that was supposed to be an N. So N1 is 164. We do the same thing with X2. The sample size is 96 and the proportion is 0.49. So when we multiply those and round, we get 47. And then N2 is 96. And then the question that we're asking is P1 less than P2? Right, that's the alternative hypothesis. And when you do this, we get, we get a z-score of negative 0.6 and a p-value of 0.275. I want you to notice that we have a negative z-score, which is fine. You're allowed to have a z-score that's below the mean. So this is saying that the difference here is about half a standard deviation below the mean. That's not unusual at all, which is why we have a pretty high p-value. And notice that when I say a high p-value, I'm talking about 27%, not 97%, right? 27% is a high p-value. So we can then make our conclusion here, which says that since the p-value is above the alpha level, we fail to reject the null hypothesis and conclude that there is not enough evidence to suggest that patients that exercise more had less falls within the last 6 months. Just a little recap from Chapter 16. If we're incorrect in this conclusion, what type of error did we make? So remember that when you fail to reject the null hypothesis, you have a possibility of making a type 2 error. So typically, we would find a confidence interval when we reject the null hypothesis and show that there's a difference. But I want you to see what a confidence interval looks like when there is no difference between the proportions. We saw the first confidence interval for what it looks like when there is a difference and P1 is bigger than P2. So now we know that there is no difference. We found that from the hypothesis test. We failed to reject the nulls, so we know that there's no difference between these proportions, between the population proportions. So if there's no difference, that would mean that when we subtract them, we get 0. So it means that when we find this confidence interval, we are going to see that 0 is in the interval. So let's find a 90% confidence interval for the difference here and just notice what it looks like. So we're going to do a 2PropZ interval. Sorry, it's on my next page of notes here. So we have that X1 is 74 and N1 is 164. Again, this will be automatically populated if you're doing this along at the same time as I am, because you already did the hypothesis test. And we're looking at a C level of 90%. And when we find this interval, we get negative 0.1439 to positive 0.06712. So notice that I get my lower bound is negative and my upper bound is positive, which means that 0 is contained in this interval. And since 0 is in the interval, that means that our interval does not provide evidence of a difference, right? It's very possible that there's absolutely no difference between these population proportions. Interpreting this is really tricky, and I've seen the mistake of people who drop the negative sign. You really shouldn't do that. But I'll show you the way that I interpreted this. So I have kind of a general interpretation where I say we are 90% confident that the difference in the true proportion of falls by patients in each population is between negative 14.4% and positive 6.7%. So I converted both of them to percents. I don't drop the negative because the negative is important when discussing which one is bigger or smaller, right? On the lower end, we're saying that those who exercise have fewer falls, but on the other end, we're saying that those who exercise have more falls. So the negative makes a difference. So I kind of put this extra little interpretation in here, little, but whatever. It says the true difference in the proportions could fall anywhere from 14.4% less patients who exercise have had falls within the last 6 months to 6.7 more patients who exercise have had falls within the last 6 months. So really we can't make a conclusion here. When you get a confidence interval like this, there's just no good interpretation or conclusion to make. Again, it's mostly because if we're going to find a confidence interval, it's because we have already rejected the null hypothesis and said that there is a difference, like we did in the first example. So we're going to do the difference between two means in the next video.